Today we want to discuss Faraday's second law of electrolysis. In the previous class, we talked about Faraday's first law of electrolysis, where we related the mass of a substance deposited at each electrode directly proportional to the quantity of electricity that passes through the electrolyte. So we further said the quantity of electricity is equal to current times time, and then we change the relationship into mass proportional to current times time, and then we convert the proportionality to equality or to an equation by introducing Faraday's constant and molar mass. We said the mass deposited at each electrode equals to the molar mass of the substance deposited times time, times current times time divided by the Faraday and then the number of mole of the electron. So that is how that is what we discussed about the first law of electrolysis, that is about the Faraday's first law of electrolysis. So today we will talk about the second law, Faraday's second law of electrolysis. So this law builds upon the first law that we just discussed, and then is relating when we have multiple electrolytic cell connected in series, as you have it this side. So we have like two electrolytic cells here that are connected in series. So the law is just talking about the quantity of electricity, just like what we have in the first law. So it said whenever the same quantity of electricity is passed through different electrolytes connected in series, as we have it here, we have electrolyte that involve silver nitrate, and then the second electrolyte is iron 3 chloride. So we have two different electrolytes in this case. So this law is related to this. So let's go again. It said whenever the same quantity of electricity is passed through different electrolytes connected in series, the masses of the substances liberated at the electrodes are directly proportional to the chemical equivalent. So there is a new word here, chemical equivalent. We can also call it equivalent weight. So what is this chemical equivalent? What does it mean? So a chemical equivalent or equivalent weight of a substance is the molar mass of that substance divided by the number of electrons involved in its half reaction. That is, we can express this as the molar mass, capital letter M, divided by the number of electron that involved in the half reaction, or so that is a chemical equivalent. So how do we relate the chemical equivalent together? So Faraday's second law is just saying that if you pass the same amount of electricity through a copper solution, or for example through silver nitrate solution and iron 3 chloride solution, the ratio of the masses deposited will equal to the ratio of their equivalent weight. So mathematically, we're saying that the mass of the substance deposited in the first electrolyte, that is in the first electrolysis, divided by the mass of the substance deposited in the second electrolysis. For example, the M1 can be the mass of silver deposited, and M2 can be the mass of iron 3, or iron deposited. So is equal to the equivalent weight of the first substance that is deposited divided by the equivalent weight of the second substance deposited. So, and then we said that equivalent weight equals molar mass divided by the electron. So it means we can change this one, the equivalent weight 1, to become molar mass 1 divided by N1 all over molar mass of the second substance divided by the number of electrons that deposited that substance. So this is all about Faraday's second law of electrolysis. So we're going to apply this in our question now. So let's look at this example problem where we have two electrolytic cells, one containing molten aluminum chloride and the other contain copper 2 sulfate solution, and they are connected in series. A certain quantity of electricity deposits 1.5 grams of copper. Calculate the mass of aluminum deposited. So we have the molar mass of copper and that of aluminum given in the question. So let's quickly have a look at how to solve this problem. So the first thing to do, which is step 1, is to write the half reaction, that is half equation for each reaction. So we deposit, if you look at it here, we have aluminum chloride, and then we want to deposit aluminum, and then the other side we have copper 2 sulfate, so we want to deposit copper, that is the solid has to be deposited in this case. So the half equation for the side of copper is going to be copper ion, Cu2 plus, copper ion from the copper 2 sulfate will gain 2 electrons. When it gains 2 electrons, it becomes copper solid. So this is copper ion aqueous. That is for the copper side. For the aluminum side, same thing. Aluminum is Al3 plus. So aluminum ion, Al3 plus, will gain 3 electrons to become aluminum solid. So these are the half equation for each reaction. So it means for copper, the number of mole of electron that is used to deposit copper is 2. So it means N equals 2 for copper. And then I can write it so we can remember N of copper equals 2. And then N of aluminum equals 3. So we have N for each one of them. And then remember, the law is comparing the masses deposited to equivalent weight. So it means M of, that is the mass of copper deposited, M of Cu, divided by M of aluminum deposited, equal to the equivalent weight of copper, which is molar mass of copper, divided by the number of mole of electron that deposited copper, so NCU, divided by the molar mass of aluminum, M of Al, divided by the number of mole of electron that deposited aluminum. Remember, what I'm doing is here, if we come back up, you will see that this is the equivalent weight of the first substance, and then this is the equivalent weight of the second substance. So the first substance in this case is copper. Anyone can be your first substance, so it can be aluminum divided by copper, and then you put all the equivalent weight for aluminum on top and that of copper down. So any one of them, any of these two ways can be adopted. So in fact, let me change it. So you know we can do it this way. And that is the mass, capital letter, small letter M, please, not capital letter M. So mass of aluminum deposited divided by mass of copper deposited equal to the equivalent weight of aluminum, which is molar mass of aluminum divided by the number of mole of electron that deposited that aluminum, Al, everything divided by mass of copper, molar mass of copper rather, divided by the number of mole of electron that deposited copper. So, in the question, we were given what? We were given the mass of copper deposited, which is 1.5 grams. So we can plug that in. So mass of aluminum is not given. The mass of Al is not given, but the mass of copper is 1.5 grams. And then the molar mass of aluminum, remember, that was given, which is 26.98 grams, divided by, remember, the number of mole of electron that deposited aluminum is 3. So divided by 3, all over. The mass of copper deposited is 63. Sorry, the molar mass of copper, 63.55, divided by the quantity of electron, that is the number of mole of electron that deposited this copper, which is 2. We did that last time. So it means, of course, we can go ahead and finish the calculation here. So the mass of aluminum that we don't know divided by 1.5 equals 8.993, I think, divided by, if you divide 63.5 by 2 to give us 31.775. So you can cross multiply and get the mass of aluminum. So mass of aluminum deposited will equal to 0.425 grams. So this is the mass of aluminum deposited. So what you need to master here, it is just the definition, that is the law, and how to convert the law to equation. So then you use that for your calculation. So this is the end of this series. What did we achieve here? We tried to state Faraday's second law of electrolysis, and then we converted that law into we represent the law mathematically, and then from that we use that equation that we get from the law to solve a problem.